So 23rd lecture on 23rd February. Good. Okay, so here now we are discussing the sine triangle PWM, and again it's more about what it is. It's about how you can understand it, what it is. So someone says that I'm using sine triangle PWM. What first question would come to your mind? What would be the first question that comes to your mind? If I ask like, okay, I'm using sine triangle PWM, what would be the first question? Say something.
Sir, width of the pulses. With how much width of the pulses would?
Sukumar, again, that's a very incorrect term what you are saying.
Sir,
What is the
frequency
correct
of
term?
carrier, pulse number, frequency of the carrier, and frequency of modulating signal.
Yes, these are some of the basic questions. So basically switching frequency gives you idea about how the carrier is, but it's not the complete information. But someone asking pulse number gives the correct idea that how your switching frequency is compared to your fundamental frequency. This gives lot of information. Someone says I'm using sine triangle PWM for pulse number 5. What you would say? Another person saying that yes, I'm using pulse number 51. You know what is the difference between the two, right? What you are going to expect in this case and what you are going to expect in this case. Qualitatively, I'm asking. You understand my point? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Correct? So when you go to industry or any other thing, you start working, let's say on your projects or somewhere, when you have motor and you want to run with inverter, first thing you have to decide is, okay, what should be the value of DC bus voltage? You cannot feed just any voltage. So many a times we see students during their MTech presentations or somewhere, they will simply keep, okay, VDC is 100 volts for 400 volts line to line motor. And some people will have sine triangle PWM where spectrum will be so bad that you cannot say that what they are doing. They will have no idea what MATLAB gives, that's all. Take that as the correct answer. Now, how will you ensure that what MATLAB is giving is correct? What is the way? Can you say? So these are the things which we must know beforehand. No, when we are going to start something, so we know that what we are doing, we are basically trying to have something like this, which is generating the pole voltage like this, and then we are going to have some order in that pulse width. The pulse width is going to change according to my modulation index or how the modulating signal is varying sinusoidally. For example, for pulse number 9, if we have to see, pulse number 9 I am saying because this is simpler to see, and then we can judge what we are doing, right? Now see, this is the case. So somewhere here is the zero crossing, which is visible. Do you see this point? And you see the width around this zero, that is almost equal, which is the indication of that you are trying to realize somewhere like zero voltage. That's why you have plus VDC by 2 and minus VDC by 2 almost equal. Same will be the case here and same will be the case here. Is it visible to all of you?
Yes, sir.
Yes, sir.
Now,
Yes, sir.
when I say that, okay, this is what I'm using and my fundamental component or modulating signal is increasing like this. So what is happening? You observe this width. This is increasing here. Somewhere it has reached the peak. Now this is reducing and becoming equal. And then the negative is going more. Here the maximum width for negative is appearing. Here the maximum width for positive is appearing. So when you are doing simulation, these are the checks which you can have in your system, whether this is happening or not. Simulation or hardware, whatever. this is matching properly or not, this is coming correctly or not. So this will tell that yes, whatever you are doing is somewhere fine. Then you can say that yes, result what I am getting should be correct because what I am feeding is correct. And then when you see VYO and VBO, that should look exactly shifted by 120 degree from previous one. You understand the point? So this is the case where I have tried to maintain even the quarter wave symmetry. So half wave symmetry is clearly maintained. Whatever is there on this half is exactly inverted on this half. Half wave symmetry is clearly maintained. But even the quarter wave symmetry, if you see about this point, you move theta on this side and theta on this side, you will find the same value of VRO. So in this particular waveform, we have maintained all the symmetries. And because this is pulse number 9, so definitely three-phase symmetry is also maintained. You can check that. You generate the pole voltage for RO, YO, BO and check whether it is matching for all three or not. You understand my point?
Yes.
So whatever you are learning over here, try to get a feeling of what you are doing here. No, it should not just become like another course, okay, learn something just for no some reason and then that's all, forget it. Understanding my point?
Yes, sir.
Correct. Now this is where we move towards the analysis of sine triangle PWM. What do I mean by analysis? Whenever we have any PWM, we should know the quality of that PWM, how it is going to perform. And when we had low switching frequency PWM, what was the metric for performance? What metrics we have set or parameter on which on basis of which we are judging everything? What is the performance metric or performance criteria?
Rated TSD.
Weighted TSD one thing, but finally what we are trying to have, how is the current TSD? And second is the torque ripple. Whenever we have motor drive application, these are two very important things. Whatever you feed at the motor terminus doesn't matter. Ultimately, you should have these two things in control. You understand my point? So anything, whatever we are feeding to motor can be judged on basis of this. How is the quality of input voltage? You can judge on basis of how good your current TSD is. So what is the best current TSD?
Zero.
Ideally 0.
0%. This is when you are feeding the motor with perfectly sinusoidal voltage. Understanding my point? And torque ripple, worst case is also 0 Newton meter torque ripple. When you have perfectly sinusoidal waveforms being fed into the machine, but this is not the case always. This is not the case when you have PWM based inverters. Certainly this is going to be some non-zero number, but how close to 0 you can bring that number to? Say someone will say I am generating some 10% of THD. Someone will say no, I am able to generate only 1% ITHD. Now which one is better? How would you judge? Of course, number wise this is fine, good. But we also need to see what is the possibility. Possibility in the sense what system you are dealing with. If you have high power system, for example, and you are bound to use low switching frequency PWM, your TSD is definitely going to be high. Something like 10-20% is nothing. Whereas if you have low power setup and you are using very high, switching frequency PWM, something like sine triangle PWM or so, you can expect something like 1% or less also. So this very much depends on what you are dealing with. It cannot be said that every system should have 1% only. No, that's not possible. It is not in our control. It is dependent on what we are dealing with. You understand the point here?
Yes.
So when we had the low switching frequency PWM, we are having, let's say, pole voltage with few notches, and we are trying to analyze this waveform. So what is the way to analyze this waveform? The way is that we go by each harmonic component. Let us say alpha 1, alpha 2 are two angles over here, or theta 1, theta 2, whatever is terminology you are comfortable with. Now, for these switching angles, we can define the voltage harmonic very easily using the Fourier transform, right? And then it is convenient that we can go by computing the current harmonic, torque harmonic, and all that. So in case of low switching frequency PWM, we are expecting, because the spectrum we have seen yesterday, it's going to be very continuous kind of spectrum. Somewhere I had drawn, okay, maybe it is deleted. So spectrum is very continuous. Continuous meaning that there is no large gap between the two consecutive harmonics. This is fundamental. There may be fifth, then there may be seventh, then there may be 11th, 13th, and then 17th, 19th, and so on. This gap is there only one or two steps which should be there in between. Whereas high switching frequency or sine triangle PWM, the spectrum will look like this fundamental and then a large gap, and then you will see something over here. So there is huge gap between the two frequencies. This is around FSW or more, and this is around the fundamental. For low switching frequency, this is continuous. बाद में आइए. So what we need to have basically when we are dealing with different systems, whether the individual harmonic is important to be analyzed or it is the set of harmonics that we need to analyze. This difference should be clear. When we are dealing with low switching frequency, these are the dominant components which we need to know. Let's say up to 19th, someone will say, okay, I will get the information about harmonics up to the 19th order, and then I will compute the cumulative effect of this. You understand my point? So we can do the analysis for 5th, 7th, 11th, 13th, 17th, 19th. We compute what are the currents, harmonic current, and then corresponding torque. Torque will be the combination of these two, right? So all these things we can analyze harmonic order wise. That's what we have done for low switching frequency. When it comes to sine triangle, it becomes difficult because first of all, yes, we can know where these are appearing. That's fine. But it is difficult to say what is the amplitude of these harmonics over here. Here this is defined very perfectly. We can say that this is 2 VDC by pi 1 minus 2 cos n alpha 1 plus 2 cos n alpha 2. With a n over here. We know what is individual component coming over here. But in case of sine triangle PWM, when we are going by analysis, we are not doing Fourier analysis of the entire waveform. The reason being there are so many switching angles in that. It's high frequency carrier, so the pulse is having several on and off instances. It's very difficult to do the way we have done for the low switching frequency case. Then we go for something like double Fourier transform or something, some other methods to only guess what possible locations these harmonics could be. You understand my point? The amplitude is not investigated much. Understand my point?
Yes, sir.
Correct. Another reason why we need not go for this kind of individual harmonic, because the harmonics are appearing very far and these are close by. It's like set of harmonic appearing very close by compared to the where fundamental is. So the effect of the combined harmonic is going to be more or less same. So there has to be a way to analyze the cumulative effect of all the harmonics which are appearing like this. That is what is the approach which is followed for sine triangle PWM. So instead of going by individual harmonic, we go by combination of all harmonics or sum of all harmonics, and which is basically called ripple. So we go by either current ripple or torque ripple and so on, which is basically sum of all the harmonic components which are appearing. Correct? Now how to do this? We are trying to compute the ripple current flowing into the system. That is what we are trying to do. So for example, let us take example of three-phase system over here. We have, let us say, the converter. Some DC bus voltage is there and this is connecting to some motor. I'm not saying this is induction motor or what kind of motor it is, but some AC motor it is. Now what we are trying to compute? We are trying to compute the current in this. And in general, let us say when we are having a system with PWM operation, we will have, let's say this is the current, the sinusoidal current. Then there will be some ripple sitting on this. So the current flowing in the machine or in the motor in the system is basically having two components. First one is the fundamental current, which is coming on account of the fundamental voltage what we are feeding in the motor. And then other is the ripple current. Fundamental current is result of fundamental voltage. So ripple current should be result of ripple voltage. You understand this statement?
Yes.
We are supposed to give a voltage which is of this nature. But instead of this, what we are feeding PWM. Understanding my point? So if we go by sub-cycle, what we are having in our carrier, we have the triangular carrier and we are having a reference signal being compared with this, say here. Reference signal means this is the value which we are trying to realize, say some m value. This value we are trying to realize, but instead of this, what we are actually having in the system, we are having plus VDC by 2 for so much amount of time and then minus VDC by 2 for the rest of the time. This green waveform is what we are feeding in the system and this blue is actually what we are realizing through this. So certainly there is error, right? We are trying to realize the value m, but what we are having, there is error everywhere with respect to what we should have in the system. This is what is the voltage error or voltage ripple, which is responsible for generating the current ripple. So you can define voltage error as the actual minus, say, the desired value. So fundamental component. This is the actual plus VDC by 2 minus VDC by 2. And then whatever is the desired value, if you subtract, that will be your error getting fed in the system. Correct? Now, we can say that whatever voltage we are having, this is also having two components. One is fundamental, another is ripple or error, whatever you want to call it. So, our fundamental current is dictated by fundamental voltage and of course the machine conditions, and the ripple current is dictated by the ripple voltage what we are feeding in the system. So if you talk about again this machine system, basically what we have here, if we draw the per phase equivalent circuit of this system, it will look like the inverter voltage, then some leakage inductance which is there in the system, and then say some back EMF generated by the motor. In case of induction motor, this is all comes as the magnetizing inductance and so on, everything combined. So ultimately you will have only the leakage over here. So for PMSM, this is simple leakage what is there on the stator winding. In case of induction motor, this will become total leakage, the stator plus rotor leakage inductance. Now this is what we are having from the inverter, say VI, and this is our say back EMF EB. And then the current flowing in the system is I. So whatever we did for low switching frequency, because if there are voltages with different frequencies, this will not interact with each other. VI is having two components, some fundamental plus some ripple. EB is having only fundamental, EB1. The machine generally back EMF will not have any kind of harmonic. That's what we assume. So this can be broken into two parts. One, where the inverter fundamental voltage is interacting with the back EMF and generating the fundamental current. So this could be back EMF, this could be the rest of the circuit, what per phase equivalent circuit you draw for the induction motor, that could be there in place of this. So which is deciding the value of I1. And the second part, which is deciding the ripple, let's say V ripple I am drawing over here, will not see any impedance on the other side, sorry, any EMF on the other side, and so this will be shorted at the other end and this will dictate the ripple current. Same thing what we have done for leakage model of induction motor. Same thing we are doing over here. Only difference from there to here is now we are talking about the cumulative effect of all the harmonics, the combined effect of all the harmonics, which is ripple. So this harmonic model is true for individual harmonic components as well as the combined ripple component. You understand this point?
Yes, sir. Yes, sir.
Clear to everyone what we are trying to do?
Yes, sir.
Now this
Yes.
composition is for individual machine. Let's say you have PMSM, so you will have back EMF and then leakage and you solve this system. If you have induction motor, you have the per phase equivalent circuit connected across the voltage. You solve that, get the fundamental. However, this part, what we are doing for the ripple, you can say is kind of common for everyone. Common in the sense only the value of leakage will change and what you are feeding. That's all. The way how you do will remain same. The method will remain same. So in case of sine triangle, we are trying to estimate or trying to compute what is the current ripple which is generated in the system. Then somebody will say, why to solve all this? Just run the simulation and see what it is. But the question will come when you go for Viva. They will simply ask, how do you know it is correct? So you should have correct explanation of what you are seeing, why it is appearing like this, which is what we will see here by the current ripple analysis. Now, we have understood that current ripple can be computed from here as this. Correct. It's only inductance over here, LL, let us say, and then the voltage ripple getting integrated over time t. Now, I have told the definition of ripple, right? In the DC-DC converter, we have discussed it thoroughly. What is the meaning of ripple? Meaning of ripple is no average value. The average value of ripple must be 0. Otherwise, it's not ripple. You understand my point? So in case of DC-DC converter, we have seen if the ripple is starting from here, it will come back to this point exactly. This cannot be different even by 0.1 ampere or 0.1 whatever small value you say. Correct? If it is different, then every cycle it will keep getting added or subtracted. Eventually, either it will flow away to a very high value or come down to 0. So that's why there cannot be any difference in the two values, which means if you draw only the ripple part of the current, that will look like starting from some point, going across the 0 axis and coming back to the same point. This is how the ripple will look like. The condition is applicable for all the ripples, whether it is AC motor or DC-DC system or anything. The average value of the ripple must be 0. Then it is, you can say it is qualified to be called as ripple only when this condition is fulfilled. If this is not fulfilled, you cannot call it ripple. You understood my point? So this is what we should get here as well. But now how to do that? For three-phase system, we have three modulating signals. Say, okay, I will write here, let us say, MR is there, say some capital M sine omega t. This is what we are having, and this is getting compared with a carrier, triangular carrier. How to compute the ripple? So for that we need to know the voltage error. Now, whatever I have drawn earlier, is this the error actually? The difference between the pole voltage and the desired output? For example, let me draw now, so then we will understand better. Okay, we are talking about computation of ripple in each subcycle, and we know that this subcycle, whatever is happening in one subcycle, that is true for the entire fundamental frequency. So analysis is true for the complete range. So we need to be little patient also now. So this is our one sub-cycle. So triangle is basically, it's not going further, but it is going here. It's coming down. Okay. So this time period, let's say TSW is our switching cycle time period. So this is only TS by 2, TSW by 2. Now we take a condition where let us say MR is having value some 0.2, MY is having value some 0.4. So MB is having value of how much? If this is the value of MR, MY, what would be the value of MB?
-0.6.
Manvendra, you keep smiling only for every statement. What's the reason?
Nothing.
You keep smiling. Whatever I say, you just give a bigger smile every time.
Nothing, sir. Actually, there is a kid in front of me, sir. That's why I.
Okay, good. Fine. So let us say the R is somewhere here. Then B is somewhere here. Okay, maybe little bit. So this is something like 0.2 for MR, for B 0.4. And MB is something like -0.6. Correct? This is one sub-cycle. And what we have assumed that TSW is very, very less than fundamental time period. So which means the value of modulating signal is not going to change much within a sub-cycle. It's almost like a constant waveform. Next sub-cycle, it may change slightly. So let us see what is happening. Now, in response to this comparison, each phase will generate the PWM voltage. So let me draw the vertical lines first, which will indicate the time intervals properly. Okay, so let us say here we have R phase pole voltage waveform VR. Then we have say VYO and we have VBO. So VRO will basically be positive up to this point, up to this interval. So it will be plus VDC by 2 up to this and then minus VDC by 2 for the rest of the duration. For B, it will be little wider positive pulse because the value is higher. So it will be positive up to this point. And then rest of the interval, it will be negative. And for B, it is very, very high negative value. So the positive pulse width will be small and negative will be large. Correct? This is what is the pole voltage. Now, when I draw the equivalent circuit, let's say this is per phase equivalent circuit, which voltage I am talking about here? This is, let's say, back EMF. Which voltage is this? Of course, inverted.
Phase volt.
Yeah, phase means what?
VRO1.
Ajay?
VRO1.
V?
VRO1, sir.
VRO1. Okay. Here I am talking about the PWM voltage, not the fundamental component.
Sir, we are talking about VRN.
VRN. We have understood different voltages, right? VRO, then VRO, VYO, VBO. Then we had the line-to-line voltages. And then we had the line to neutral voltage. What is the difference between pole voltage and line to neutral voltage?
Zero sequence.
1/3 of that line voltage. Neutral
What is
voltage.
the difference between pole voltage and line to neutral voltage?
Only common mode
The
offset.
only-
signal.
Yes.
Only
Common mode voltage is there with this line pole voltage.
Common modes are missing from the line to neutral voltage.
Neutral.
What is definition of common mode voltage? Sum of all voltages should be 0, which is basically the balanced power supply. But if you add VRO, VYO, VBO, is it going to 0?
no, sir.
No.
Sir.
Because there is some common mode present in this that we have seen for the 6-step voltage, and this is true here also. So when I draw equivalent circuit of the system, this is always with respect to the line to neutral voltage. It is the line to neutral voltage that decides the currents in the system, whether the fundamental or the ripple. However, every analysis, if you take in terms of fundamental, it is same for VRO and VRN. But see the difference. If you want to subtract the average value from this and do the analysis, it will be wrong, because there is some common mode sitting on all the voltages. You understand my point? So we need to compute VRN. Now, how to compute VRN from this? How to compute? It is 1/3 of VRY minus VBR. So effectively, if you break that in terms of pole voltage, you will get this twice of VRO minus VYO minus VBO divided by 3. This will give you the value of VRN, what you are feeding into the system. You understand my point? So let us compute that now. These intervals are important because this is where the pole voltages are having transition. That's why these need to be drawn properly. If you make mistake, then something incorrect will come out as analysis. So let's say here I am trying to draw my VRN, the line to neutral voltage. So according to this, 2 VRO minus VYO minus VBO, what will be the value in this interval? During this interval, say this interval is T1, then this interval is T2, this is T3, and this is T4. So what is the value in during T1?
0. 0, sir.
0, because twice of VRO minus VYO minus VBO, and all three are having the same value. So this is basically 0 in this interval. Okay, next one.
2.
What is 2?
It's twice VDC.
VDC by 3.
So twice VDC by 3.
3.
Where is twice VDC coming? How are you getting
Sir, VDC by 3.
Yes. Clear to everyone, or somebody is getting 2 VDC by 3?
It's a VDC by 3.
Correct? Now, during this T3, during the T3 voltage, T3 interval,
Minus VDC by 3.
yes. Everybody getting that?
Yes, sir.
And then T4,
0.
0. Does this look logical to you or not? What do I mean by logical? See, here what is happening during interval T1, you have connected the top switch of the R, top switch of the Y, top switch of the B. So which means your load is shorted with the positive DC bus, which means the voltage applied on the system should be 0. You understand my point? Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Looks logical? This is connected, and then this is connected. All three top are connected. So which means RY line to line is 0, YB line to line is 0, and BR line to line is 0. So what is the effective voltage applied on load?
0.
0. Same with here, when all three are negative. When all three are negative, what should be the voltage applied to the machine? Effective voltage. All three line to line voltages are 0. So which means effective voltage is 0. You understand my point? This is where in between we are applying some voltage, say plus VDC by 3 or minus VDC by 3. Effectively, the voltage is applied only during this T2 and T3. Okay. Now, what is different between the pole voltage and line to neutral voltage we have seen? The difference is common mode voltage, that is gone. Now what is same for both?
Fundamental.
Fundamental. So when we are applying this voltage plus VDC by 2 and minus VDC by 2 here, what is the voltage we are trying to realize?
Pole voltage.
What is the value of voltage we are trying to realize here?
So 0.2 in R.
VDC by
Exactly. This is what is the MR value. So our pole voltage average value is what? MR times of VDC by 2. Are we not doing that? Yes or no? Say something.
Yes, sir. We are doing that.
Correct or not?
Yes, sir.
This is the sine triangle you are learning from past 3-4 days, right? What voltage you are trying to realize over here? M times of VDC by 2. What value of M is there? 0.2. So effectively this pole voltage what we have applied is trying to get a value of 0.2 times of VDC by 2. Or you can say 0.1 VDC. Isn't it? Yes or no? Say something.
Yes, sir.
So what is the voltage we are trying to realize here in VRN?
They're also same thing,
Same
but in a
thing.
different way.
Same this fundamental, yes, sir.
In a different way means only the common mode is gone. Correct. But the average value will remain same. What it will remain? It will remain 0.1 VDC. It will remain this. You have not changed the fundamental, you have changed only the common mode you have removed, that's all. Average of this is same as what you have got earlier, average of this. You understand my point or not?
Yes, sir.
Now,
Yes, sir, yes.
if this is the actual voltage, okay, let me draw this one in red, the average value. If black waveform is the actual voltage and red one is the desired, then what is the error? What is the error?
0.23 from the top.
No. First, you tell the definition of error.
Difference between
Actual
pole
minus
voltage
fundamental.
and
Difference between the actual minus desired, right? That much error we are creating on the system. That much of error voltage we are feeding, which is not necessary to feed. But what to do? We cannot help that. It is going because of the PWM action. So let us write the error voltage. Let's say here. Now, what is the error voltage during interval T1?
Minus 0.1 VDC.
Minus 0.1 VDC, say somewhere here. What is the error voltage during T2?
0.23.
0.23 something, right?
Yes, sir.
Somewhere here, let us say. And this is positive. Then what is the error during T3?
Minus 0.43.
Hmm?
Minus 0.43.
1, 2, 3, 4, and then 3 somewhere here, let us say. And then during T4, again it comes back to minus 0.1 VDC. This is the error voltage what you are feeding in the system, or you can say the ripple voltage what you are feeding in the system. Now the ripple current coming in the system is because of this voltage here. You understand my point? How the analysis for sine triangle PWM has come down to this. We have the sub-cycle information, we know the modulating signals, we have come to the pole voltage, from there the line to neutral voltage, and then subtract the average voltage which is getting realized, and then you get what is unnecessary that you are feeding in the motor. This is unnecessary, this is not required to be fed, but this is going because we cannot help that. So this is what is the VRM which is fed to the machine. This is the leakage model of the or harmonic model of the motor. So now what is current? Current is simply integral of this complete thing VRN over this interval 0 to t. So over this entire interval. But we see that there are different segments where VRN value is changing. Say here it is minus 0.1 VDC, here it is plus 0.23 VDC, minus 4.3 VDC, minus 0.1 VDC, right? So what we can do, we can break all this in 4 segments. So we can write one by one. Say segment 1. So the definition of ripple, what we have said, it cannot have any average value, which means what? It has to start from 0 and it has to end up at 0. If because of numerical error you are getting some non-zero value, that's a different thing. But the definition of ripple is you are starting from 0 and you are ending at 0. In between some non-zero values will come. So we can write, let's say current during this interval T1, it can be written as some I, which is basically starting with 0. So we have minus 0.1 VDC times of dt, and this is going from 0 to T1. Correct? Or you can write current value I1, which is the final value of the ripple. This would be a linear graph. So this will be minus 0.1 VDC by L times of T1. So our current will move in the negative direction up to some current value, say I1. Understand my point? Now, during the interval T2, it will reach to value I2, which will be basically I1 plus. Now the starting point is different. It is starting from I1 and then it will go in this manner, plus 0.23 VDC by, sorry, L is already there. So dt, this is 0 to T2. The interval is T2. So this is basically I1 plus 0.23 VDC by L times of T2. Similarly, the next one will start from I2 and it will move to next value, which is I3, which will be this. And then I4, which will basically have I3 plus, or rather minus, these will be values of the current. So I4 must be 0 finally. It should come back to 0 value. So how the ripple would look like? It will move in the negative direction, then it's going in positive direction, and this T2 interval is pretty large. And the slope also, if this is 0.1 VDC, this is 0.23. So double slope of that. So let's say here or somewhere here, let us say. Then you have almost 4 times of slope. So it will steeply reduce and then it will gradually move to 0. You understand the point here?
Yes, sir.
This will
Yes,
be the
sir.
nature of current ripple in your system. Okay, I will remove the extra line here. And the peak to peak ripple will be this. And these values are computed. T1, T2, T3, T4 are also computed. No, every value VDC or this, every interval is now computed on basis of modulating signals. How do you compute these T1, T2, T3, T4? Again, we can go back to our similar triangle method. This interval, whatever is coming over here, this or this or this or this, it's all associated with particular modulating signal. So you can equate, let's say if I draw in green this triangle and this big triangle, these two are similar. So the ratio of this height and this height is basically the ratio of this base and the whole base TSW by 2. So you can write T1 is nothing but TSW by 2 times of minus 1 plus MB, or minus 1 minus MB rather, by 2. You are seeing that? Similarly, you can equate this. Okay, and let me mark in blue this triangle, what is coming over here, and the biggest triangle in this. So that will give you information about T2 and this with respect to this height. So you can write T2 as TSW by 2, then MR minus MB divided by 2. You are getting my point? Similarly, T3 you can write, which could be, say, this small triangle compared with the bigger triangle. So this could be TSW by 2 times of My minus Mr by 2. And then T4 could be simply TSW by 2 minus T1 minus T2 minus T3. Or you can compute from here. Both ways it is fine. So we have information about the time intervals on basis of the modulating signals.
Sir,
And then
T1 is 1 minus MB.
yeah, so MB is negative, right? It will become positive eventually. It's just the difference between the two.
Sir, then like in that expression we get negative now, sir.
Okay. Time cannot be negative, that's what you are trying to say. So 1 minus MB we can write. So this is magnitude of MB then, no? The difference between the two only. Correct? Is that clear to all of you? So this is how we compute the ripple, what is going to come on the system because of our sine triangle PWM. If you see the ripple, I will show you tomorrow. This will be the nature of ripple which is going to come on the current. And peak to peak ripple is going to be of, no, it will increase gradually and somewhere it will become maximum, then it will reduce to minimum and so on. So where is it maximum? That is the interesting point we should know. But before that, what I want to conclude over here in this part, that you try the values before tomorrow's class, you try to work out these numbers. Let's say you take these modulating signal numbers and you try to work out these numbers, say T1, T2, T3, T4, and then I1, I2, I3, I4. So basically this value of entire thing. Just try to work it out yourself before coming to class. Understood my point? Now the analysis which we are doing over here for one subcycle, this itself will repeat itself for all the subcycles coming over the entire fundamental cycle. So which is why doing analysis from one is sufficient. Maybe now we can look for the worst case. So worst case meaning what? If current ripple is dictated by voltage ripple, you will see worst current ripple only when the voltage ripple is worst. Understanding my point? You will witness worst current ripple only when your voltage ripple is worst or highest. Voltage ripple worst could be when you don't want to generate anything, still you are applying PWM. For example, at the zero crossing of the modulating signal, what you want to realize? You want to realize zero voltage. But how will you do? You will apply plus VDC by 2 for half cycle and minus VDC by 2 for rest of the time. You understand my point? Which means here anything whatever we are doing is unnecessary. We should not apply actually anything because the value required is 0. But still we are applying plus VDC by 2 for this half time period and then minus VDC by 2 for another half time period. That's all unnecessary. This is what we call as the worst case voltage ripple. The entire thing what we are feeding here is only ripple. There is no useful component in this with respect to R phase. And which is where the R phase current ripple will also be worst, maximum. So once you try running the system or the simulation, very interesting thing you will observe is that, say, this is your voltage and you try to have some current, let's say it is lagging by almost 90 degree or so. What you will observe that on this current, there will be ripple everywhere. But wherever this zero crossing comes, suddenly the ripple will be highest. So at this point, it will be something like this. At this point, it will be something like this. In all other places in between, it will be small ripple somewhere, but suddenly it will maximize. So here it will be minimum because you are trying to realize the maximum voltage. Here also it will be minimum, and then between it will keep increasing and it will be maximum here, then gradually reducing, and then it will increase again to maximum. This kind of pattern you will see in the current ripple on the motor current or somewhere, whichever you run with this kind of PWM. You understand what I'm trying to say? This is another identification that your PWM is going correct. Whenever you have zero crossing, you have the worst case voltage ripple, and so you have the worst case current ripple. So irrespective of the phase, wherever this zero crossing of voltage is coming, exactly at that point you will see the worst case current ripple. This observation you should make when you are doing some of the lab exercises in simulation. Understanding my point?
Yes, sir.
Fine. So apart from this exercise, what you would do one more exercise, that take value of MR equal to 0 and try to rework again all the things. Now if MR is 0, what could be the value of MY and MB?
Sir, equal and opposite.
But what?
0.5 minus
0.5 minus 1.
That you are saying when you have no somehow assumed that modulation index is 1. Okay, don't assume modulation index 1, or even if, okay, you are free to assume that, but maybe some reasonable number could be 0.8 modulation index. Okay, so just try to work out how the ripple looks in case of this MR equal to 0 value. These will be interesting things which you will do in this course. Of course, this will be part of assignment and exam as well, but which is where this makes much more important for you to do this analysis. Fine. So I am giving hint for the most important question also for MTE. Be careful. Good. Okay, any doubts in this part so far? Tomorrow we will see some examples how this is coming. Some simulation I will try to run, not on Simulink but through MATLAB file, .m file. Yeah, any doubts in this? Fine, clear to everyone? So do these two exercises you do, and you will get a better feeling of what I'm trying to say so far. Now this is how, before you are going to run the system, you can get idea of what amount of ripple you are going to see in the system. Now two things are necessary to observe over here. What are the two things? First thing, that you have only two voltage levels in this system. When you are dealing with two level inverter, you have only two voltage levels, plus and minus. So because of that, we are encountering only extreme values of this plus VDC by 3 minus VDC by 3. And so we have some amount of ripple coming over there. So as you go for multi-level inverter, this is the first difference you will see. This will change and it will become in multi-level waveform. So you need not go on the extreme values always. Let's say 3 level, you will have only plus VDC by 2 and 0, or minus VDC by 2 and 0. So of course this error in voltage, what we have said, this error in voltage here will come down. Do you see that? So amount of error voltage what you will be feeding in the system with a multi-level converter will be much lesser compared to the two-level inverter, which is why we see a better THD performance for multi-level converter. Understand my point? Because we are not giving so much error compared to what we have to feed actually. You go for 5-level converter, this will be even better. Go for 9 level, 11 level, 13 level, this all will become very, very close to what you want to feed. And that is why the voltage error will go to almost negligible value, and so is the current ripple. You understand the point? So we always say that multi-level converter performs better than two-level converter. This is the reason what you are feeding is better compared to the two-level converter. Am I clear?
Yes, sir.
Yes, sir.
So I will not do the multi-level converter analysis here. So because more we need to go towards drive, so that I will keep to this only. Another observation if you make, let's say we take only two-level converter. Okay, and compare two different systems. I have talked about high power, low power systems, right? So the difference between high power and low power system would be only two things when you are computing the current ripple. Let's say here. So for high power system, we will have leakage value of inductance, very small number. Correct. Let's say this could be 1 millihenry or so. For low power system, this will be something like say 5 or 10 millihenry it could be. Another difference would be that high power system will have more DC bus voltage, say 2000 volts DC bus or more. Here, the low power system will have generally 700 volts or 800 volts, something like that. Now you see for the same converter, two-level converter, if your leakage inductance is lesser, you are going to see a higher peak in the current ripple. If your DC bus voltage is more, further higher peak you are going to see. So that is why peak to peak ripple is going to be worse, always going to be worse for high power system compared to low power system. Low power system you have lesser DC bus and higher leakage, which both are constraining the peak to peak current ripple to be within some limited value. Whereas high power system we have both the values which are boosting the current ripple. DC bus value is high, so the slope will be much higher. Leakage is also lower, so this will be further higher. So same ripple what I have drawn, if you say that this is for low power converter, I can draw the high power converter ripple, it will look like this. That is why for high power system, we cannot have THD value very small number. It will eventually be something like 10%, 20%, 30%, sometimes even 70%, 80%. That's the reason. Any confusion here? Any doubts?
So the value of C1 will it not be PSW by 2 into 1 minus MB by 2?
It's only the difference we are trying to take over here.
Yes, sir.
Yeah, this height only we are trying to take.
Only height, right?
Yes. So which is what this triangle is there, which is similar to this bigger triangle. So it's only the difference that matters. Am I clear here? as far as the sine triangle PWM is concerned, there is no direct analysis for the torque ripple. What they say that torque ripple is somehow related to current ripple. You try to reduce current ripple so we can have better torque ripple. There is no special way of dealing with torque ripple here. Actually, there is no way to deal with torque ripple also. The only way you can reduce the current ripple is basically by increasing the switching frequency, which means you are reducing the time interval TSW. So every interval T1, T2, T3, T4, if it gets reduced, obviously the current ripple will be lesser. That's why for higher switching frequency, we see lower peak to peak ripple, because each and every interval becomes small. So the only way to improve current ripple in sine triangle PWM is increase the switching frequency, or in other words, reduce all these intervals. So today we have talked like wide variety of systems: 2-level, multi-level, high power, low power, high switching frequency, low switching frequency, all that, right? This is how you can correlate this with everything. You understand the point, right? Now, only question that no one asked for doing this analysis is that what switching frequency we should consider. You need to know the value of TSW, right, to compute I1, I2, I3, I4.
Yes,
So
sir.
take something like 3000 Hertz FSW. And because I have set the modulation index of 0.8, keeping V by F, the fundamental frequency will be 40 Hertz. Say that's the general way. Just try to compute, see how much you are getting, how much you are able to solve. Any other thing do you need to know in this? You need to know the leakage also. You need to know the VDC also. Okay. So as of now, you take leakage something like 5 millihenry, total leakage I am talking about, and VDC of 800 volts. Fine. All the data are now complete for your analysis.
Yes, sir.
So let us see tomorrow how it goes. Fine. Shall I stop here? And apply these concepts. No, whenever you are doing something, just apply and see whether you are getting the correct thing or not. This analysis is very, very useful, whether you are working for motor drive or grid connected system or anything. This is applicable everywhere. Fine. Okay.
Yes, sir.
Let's
Yes.
stop over here if there are no further doubts. If there are any questions, ask. Otherwise, we will stop. Now Tejdeep is smiling. Yes, Tejdeep.
Not in this.